Okay, so those were the basics of the Solow model, or the Solow-Swan model. The kind of main components here are, one, the neoclassical production function, and two, most importantly, I think, is that we're assuming full employment. Okay? And so those two things taken together mean that output is going to be determined by supply, and growth in output is going to be determined by the growth in the factors of production. Growth in capital and growth in labor and growth in technology, all kind of filtered through this neoclassical production function. This production function we saw already in the theory of the firm. So now let's kind of go through the Solow model, its basics. And just as a warning, there are kind of a few mathematical derivations in here. Nothing terribly complicated, but just prepare yourself for that. Okay, so we start with our usual production function. Okay? But we want to work in per person terms. Okay? Why? Because, one thing we might be interested in is the growth in output per person. You could still have growth in output without having growth in output per person. Now, in general, economists will look in growth in GDP per capita. That's kind of what we're looking at here. We want to be looking at output per person, or y divided by n. And we're going to call that little y. Okay? In general, in what follows, when we have lowercase variables, that's going to be the per person equivalent. And I'll always point them out as we go. Okay, so how do we get an equation then for per person output, little y? Well, luckily our constant returns to scale assumption comes in handy here. And here's how. Okay? So little y is just equal to big Y over n. Saw that here. This is the same as, we can plug in our production function. Okay, so that's z times f, k, and n, which we see here. And again, just all divided by n, or multiplied by 1 over n. Now, because of our constant returns to scale assumption, this line is the same as this line, right? That is just the definition of CRS, is that if I multiply both inputs by some number, in this case 1 over n, it's the same as multiplying, just the entire production function by 1 over n. Just the definition of constant returns to scale. Okay, let's follow this through. So n over n just becomes 1, and k over n becomes capital per person, little k. And just to simplify the notation, let's just call this new function little f. Okay? Now this is intuitive still, right? Here on the left-hand side we have output per person. On the right-hand side it's a function of capital per person and z, right? The more capital per person I have, the higher will be output per person. Now, if we plot it, it looks something like this. This is straight out of the textbook. Okay, here's capital per worker, capital per person, little k, and here's output per worker. And notice that it just looks exactly like our usual production function, right? It has these kind of diminishing marginal products. In this case, it's a diminishing marginal product of capital per worker, but the logic is the same, right? Remember that diminishing marginal products are coming from this too many workers per machine, this congestion effect. Well, that's the same thing here, right? Now we're just talking about capital per worker. And so the higher is capital per worker, the higher is the number of machines per person. And so we're assuming this congestion effect. As we add additional machines per worker, each additional one increases output by less. Now, you'll notice here that the slope, in fact, is just the marginal product of capital. That's big K, not little k. Why is that? Well, here's the derivation. Again, I warned you, there's going to be several derivations in this section. And in general, well, I won't say that. I was going to say, in general, you don't have to memorize how to do them, but, you should kind of at least understand them. So why is the slope of our production function, our per worker or per person production function, why is the slope the marginal product of capital? Well, okay, let's work through it. Here's little y. Okay, this is just the definition we saw before. Now multiply and divide this input by n. Okay, this is just multiplying by 1, so it doesn't change anything. Multiplying and dividing by n. Okay, this just becomes capital per person times n. Fair enough, makes sense so far. Now, let's take the derivative of little y with respect to little k. Okay, well, it's going to be the following. So this 1 over n appears again, right? And the z appear again because they're multiplying this entire function. And then, because of chain rule, it's just the derivative of f with respect to its first argument. So that's f subscript 1. Okay, that's the derivative of f with respect to this whole argument. And then multiplied by the derivative of the first argument with respect to little k, which is just n. Okay? And then, of course, these n's cancel out. And you're left with d little y over d little k is z times the derivative of f with respect to its first argument. And as it turns out, that's just d big Y, d big K. Or it's the same as the marginal product of capital. Why is the slope decreasing? Okay, that's what we kind of talked about already. So in particular, it's diminishing marginal product. We spoke about this. That's why as we increase along the production function here, we add capital, the slope is decreasing. Okay. And recall this is due to our congestion argument. So adding more capital for a given set of workers results in fewer and fewer workers per machine. And just, for the sake of argument, consider how this differs from constant proportions. Okay? So in the constant proportions technology, I would have something like this. A straight line up until we reach our particular ratio that we desire, and then after that, no additional benefits. Okay, let's talk about the dynamics of the model. Okay? So in particular here, it's going to define S in the same way as we saw before. Little s will be the savings rate. Delta is going to be the rate of depreciation. Okay, that means how much capital depreciates each period. Or put another way, we assume that there's some wear and tear on our capital. And so, between this period and next period, some of my capital wears away and it's no longer useful. It breaks down. Okay, that's the rate of depreciation. N is going to be the rate of growth of population. And then one more thing. I'm going to call dot x the derivative of a variable with respect to time. Okay, or you can think about this as how much x changes between two periods. Okay? Okay, with that, well then, how does capital, aggregate capital, change over time? Okay, so in other words, what's the derivative of capital with respect to time, or how does it change between two periods? Well, it's going to grow by I. This is the amount I invest. Okay, so if I invest, I purchase 10 more machines, then my capital grows by 10 machines, and then minus how much of my capital depreciates. Okay, so if the depreciation rate is 10%, that means between today and tomorrow, 10% of my machines break down and they're no longer useful. I throw them out. Okay, so that's how capital evolves from period to period, how it changes. Now, we can kind of, add to this here. So what's investment? Well, it's just little s, the savings rate, times y. The assumption here is that people, consumers, are saving. And when they save, their savings become investment. Okay, so I'm saving, and the way I'm saving is I'm, effectively purchasing machines. And okay, fine, so then let's add our production function here. So instead of y, big Y, let's put our aggregate production function. Now, remember we want to work in per worker terms, per person terms. So I just took this from the last slide. So we want it to be in per worker terms. So okay, let's see what we can do. So here comes another derivation. So let's divide everything by n, okay? So I'm dividing both sides by n. That's all I've done here. So what happens on the right-hand side here? Well, we already saw what this is. This just becomes, forgetting about the s for a second. If I multiply 1 over n times z times the production function, it gives us our little production function, i.e. output per person. So this term just becomes savings rate times output per person, which is given to us by our output per person production function. This term is just k over n, or little k. Great. So far, so good. Now, the problem is we want everything to be in these per worker terms. Dot k over n is not the change in per worker capital. It's the change in capital divided by the current stock of workers, which is different. So I take it here to the next slide. Now, we want dot little k, or the change in little k between two periods, the change in per worker capital between two periods. Can we get it into the equation somehow? Well, here comes another derivation. So recall that dot k, the change in capital between any two periods, is just the derivative of capital with respect to time, t. Okay? Let's see. We'll kind of put in here now. So instead of little k, let's put big K over n. That's just the definition of k. And then let's work through the math. Okay? What's this? Well, I have two terms here which change with t. Okay? K changes with t, and so does n. So I have to use chain rule. Okay? So in particular, I'll first take the derivative of k with respect to time multiplied by 1 over n. That's this. And then I also have to consider the derivative of n. Since it's in the denominator, it's a minus, and I square it, okay? And then times the derivative of n with respect to time. Okay, if you just apply the chain rule, go through the steps, this is what you end up with. Now we can kind of rearrange here, okay? So we have an n squared. Let's separate it into two n's. Okay, so that gives us this. And then let's just apply our definition. So k over n just becomes little k. And n dot over n is the growth rate of labor, which we already defined to be little n. Okay, this is just the definition of the growth rate, and I call that little n. That's the growth rate of population. Okay, there's our derivation. Notice now that I have this term, big K dot over n, here and here. So if I rearrange this equation, I take this nk to the other side, I can just plug that in onto the left-hand side of our equation above. So let's do that. Here's what we end up with. And finally, I can move this nk to the other side, and I end up with the following. This is now the growth of capital per worker between any two periods. And although it was, the steps to get it were kind of confusing, the intuition is simple, what we end up with. Okay, here's the intuition. We have two terms here that define the growth rate of capital per worker. One is the level of investment per worker. Okay, this is just the savings rate times output per worker. So you can imagine that, imagine each worker is literally earning the output per worker, little y, and each of them is saving amount s. Okay, then the addition, the amount of investment per worker is just s times little y, or s times our production function here, our per worker production function. So this is just investment per worker. This other one, delta plus n times k, is the amount of capital per worker we lose, first due to depreciation, right? Some of it depreciates between today and tomorrow. I have to throw it out because it's no longer any good. Okay, and then some of it, quote unquote depreciates because of n, the growth rate of the population. What do I mean by that? Well, you can imagine that as the population grows, there's more and more workers, okay? And so if capital didn't change at all and n grew, there were more and more workers, just by definition, I now have a lower amount of capital per person, okay? Because there are just more people now for the same amount of capital stock. And so in a sense, then we lose some amount of capital per worker just by the number of people growing, okay? Just because we now need to give more machines per person. So that's why n appears as a negative in this equation. The faster is the rate of population growth, the slower will be the growth of capital per worker, all else equal, just because there are just now more people I need to give machines to. There's now just more people that I need to supply with capital. Okay, here's our graph, and this really gives us kind of the intuition for everything here, okay? I've now plotted these two things on a graph, okay? So in one case here, we have, this is just our production function multiplied by S, okay? Our per worker production function multiplied by the savings rate S. Since it's just being multiplied by a constant, it just looks exactly the same as our production function, okay? On the other axis here, I just have a, or sorry, not the other axis, as my other line, I just have a straight line here, which is just n plus delta times k. Okay, again, this is kind of like the amount of capital per worker I lose due to depreciation and population growth in each period. And it's increasing because, you know, for example, if you think about depreciation, the more capital I have, the more I lose due to depreciation, because a constant fraction of it is depreciating. Okay, great. Now let's think about how the model behaves. Imagine I'm at point K0. I have this much capital per worker. Well, let's look at what this means. It means that savings per worker is greater than the amount of worker I'm losing due to depreciation in N. Okay. Savings is greater than the amount of capital per worker I'm losing due to depreciation in N. What does that mean? Well, just from our equation from before, that means that this is positive, and therefore capital per worker is growing. Okay, so if I'm ever here, it means that capital per worker is going to move in this direction, to the right. Okay, just because savings per worker is greater than the amount of capital per worker I'm losing. Now the opposite is true at K1 here, right? At K1, the amount I'm losing in this period is greater than the amount I'm investing. And so as a result, little k, or capital per worker, is going to be shrinking. It's going to be decreasing. I'm going to be moving in this direction. So recall that Solow wanted to make a model that was stable. It wasn't, growing exponentially or leading to unemployment and so on. It was stable, unlike Herod and Domar. Well, as it turns out, he does that, right? And here's why. This point here, the intersection of these two lines, is a stable equilibrium. What do I mean by that? Is that capital per worker neither shrinks nor grows at this point. It's stationary. It's not changing. Okay? Its growth rate is 0. And the condition for this equilibrium is just that these two lines have to be equal. Or put another way, the amount I'm saving per worker has to be equal to the amount of capital per worker I lose per period. This is our condition for equilibrium. And now, since output per worker is just given by our production function here, our per worker production function, then stability of k, little k, implies the stability of little y. Or put another way, since little k isn't growing, therefore little y also isn't at this equilibrium. Okay? In other words, all else equal, ceteris paribus, y is not growing at k star, and we have an equilibrium level of output, little y star. That is, an equilibrium level of output per person. Okay? So at the equilibrium, neither capital per worker, or capital per person, or output per person are changing. They're both constant. And again, what's important here is that this is very different than this instability we saw in Herod and Domar. What about big K and big Y? Okay, so we saw that little k and little y aren't changing. So what does that mean about big K and big Y? Well, let's think about it intuitively, and then I'll do yet another derivation, okay? Intuitively, okay, let's think about big K. We know that capital per worker is not growing, okay? At the equilibrium, capital per worker is not growing. Capital per worker is just given by big K over N, okay? So for this to not be growing, that suggests that K and N, big K and N, must be growing at the same rate. Okay? If they weren't, say K was growing faster than N, little k would be growing. Vice versa, if big K was growing slower than N, little k would be shrinking. Okay? So the fact that capital per worker isn't changing just suggests that the amount of machines we have must be growing at the same rate as population. So as population grows, we're also growing the amount of machines to give to them And so the two are kind of growing at the same rate. Right, which is what I say here. We need k to increase as much as n so that workers have the same number of machines each, such that little k is constant. Okay. What about y? Well, this again comes from our constant returns to scale assumption, right? So both k and n, now we know, are growing at the same rate. They're both going to be growing at the rate of population growth, little n. Y is constant returns to scale, which means that if I increase both k and n, both of its inputs, by the same factor, then output will grow by that factor. It will also increase by that factor. So put another way, if I multiply both k and big N by some growth rate, then y also must increase by that growth rate. And so not surprisingly then, y must also be growing by that same rate. So this is kind of nice, right? We get this property now where everything's growing at the same rate. Okay? Big K is growing at the same rate as N, which is growing at the same rate as Y. Big Y. Here's the derivation. So recall that dot x is just the derivative of x with respect to time for any variable x. Okay, or it's just xt plus 1 minus xt. And so dot x over x is just equal to, just divide this through by x, and that's just equal to the growth rate of x. I kind of referred to this already on an earlier slide. Okay. The important thing here is just to notice that dot x over x is just the growth rate of x for any variable x. Okay? That's what's important. All right, let's work through this then. So what's the growth rate of k? Well, k is just n times little k. Okay, and remember I said that when we have a product like this, or a quotient, it's true that the growth rate, I'll just show you the next line, it's true that the growth rate of capital then is going to be equal to the sum of the growth rates of its two components here. So the growth rate of k, big K, is just equal to the growth rate of n plus the growth rate of little k. That's just true by definition of growth rates. Okay, the growth rate of little k is 0. Sorry, that's the same line again. And so that means that big K is growing at rate n, the same rate of growth as population. So this is just the derivation for the intuition I showed you before. What about the growth rate of y, of output? Well, again, this comes from this constant returns to scale assumption, right? If I multiply both n, labor, and capital by the same amount, we'll say little n, the growth rate of population, well then output must also increase by that same amount. Therefore, it's growing at the same rate as its inputs.